Right, let's have a look at some physics, shall we? This is the exam prep side. We're going to do, these are the kinds of questions I've taken and adapted them, thought up some of my own, but they're essentially from and modeled on old tests and exam papers and things like that from a myriad of different sources, okay? So first of all, you've downloaded by now and we should be able to go through question 1. Please remember, okay, the deal with these is, obviously you can look at whichever section you like, but make sure that you've gone through them and we're going through together, and where you're not sure, take down what I've done, have a look at it, let's go through it step by step. Because in essence, do you know what? You're on the road here of a science majors, like in physics and chemistry, so it's actually not as tough as people make it out. I'm not going to say it's easy, that would be denigrating the subject, but it really isn't as tough as some people think. It's a lot of logic, all right? And that's what you got to get. I'm going to often say you must become this. Think what happens, right? You know a ball bounces. We're going to look at things like that in this course, okay? First of all, the question is on waves and things like that. And the first question says, on the following diagram, label the parts shown and basically just say what they are. They're in phase, out of phase. In other words, they're talking about a wave, aren't they? So how do we represent a wave? Well, we represent a wave, generally speaking, and it looks something like that, doesn't it? And yes, it goes up as high as it goes down. And we call this piece up A, and the piece down over there is A, and they equal, for our purposes, right? That A is equal to the amplitude. Okay? The A is the amplitude. It is not the height, all right? If you're thinking about being in the sea sitting there, when a wave comes past, kind of the height is that there, isn't it? So let's say the height, okay, it's not a term we use, but just think of it as that is equal to 2 times A, all right? It's twice the amplitude, right? So next step is to say, right, they said to us, label the points 1 and 2. What is point 1? Well, it's the distance. I've got to draw mine a little bit longer, okay? And it goes there and then back down. It's the distance between a crest and a crest. This is called a trough. This is called a crest, okay? So what are we saying? Okay, we are saying that I've answered this. That is point E. Point E is a trough on our thing, right? And the crest is A and B, all right? A and B are crests, all right? What is it called if you measure the distance from crest to crest? It is called the wave length. And it's got a special symbol. It's called the Greek symbol lambda. Okay? All right? Might be L-A-M-D-A. I've seen it spelled like that. Not often, but that could be typo. But whatever, it's lambda. Okay? So, we've basically answered question 1. Okay? We've put all the pieces in of it. Right. What else have we got? Next is question 2. All right? Question 2, consider the following wave, moving left to right at 2 meters per second. Now, can you see they've given us a little drawing, okay? I'm just going to quickly draw it in over here. They've given that. Then it goes back up. Then they've given us another piece going up top there. Then they've given us a piece going down again. So they've drawn a few pieces of this wave, haven't they? All right? And then I'm going to draw it back down to there again, all right? Granted, mine isn't as nice and neat as the one that you've got. And they've said that this over here is 10 centimeters. This is 2, 4, 6, 8. 8 and 10. All right? And they've asked us, okay, and it is traveling this way with a velocity equal to 2 meters per second, moving from the left to the right. It doesn't really matter which way you do it, but let's just keep it left to right. So it's moving that way at 2 meters per second. Now they've asked us a few things about it, right? Okay, first of all, let's have a look. What did we say? What is the amplitude? Right, now let's look. The amplitude is this little bit here, isn't it? Okay, so question 1 was what is the amplitude? And we would say the amplitude is equal to 10 centimeters. But in physics, what do? In physics, we go everything kilograms, meters, and seconds. 10 centimeters doesn't fall into that. It's not meters. So we have to convert first of all. Guys, it is critical when you get the information and you write it down. First of all, okay, convert the things into kilograms, meters, and seconds. Don't leave them. The reason being is that when you're hurrying through a question and something is given at, let's say, 60 kilometers an hour, your brain doesn't always recognize the kilometers per hour and it puts in a 60. All right? There's a lot of mistakes that are caused by virtue of not doing the conversion straight off, right? Okay. The second thing, obviously, in physics, and I'm going to reiterate it time and time again, do a drawing. The drawing allows you to focus on what you know, what you're given, and what is happening. Okay? And as you solve the problem and get the answers like wavelength or amplitude or whatever, put it back on your sketch because you're going to need it for the next one and the next one, particularly when we get to electric circuits, right? You're going to need it. Okay, so what do? We say, right, what is the amplitude? Okay, then they've said to us, okay, what is the period? All right, how do we define the period? Okay, the amplitude is 10 centimeters. I have to convert that is 0.1 meters. 2, what is the period of this? Okay, the period is 1 over the frequency. Okay, but the period is the time taken for one wavelength to pass you, isn't it? So we need to go back to the diagram and say, right, let us find a wave. Well, first of all, this particle here was at rest, right? It's not moving up or down. Then along comes a wave and it went up and then went down, and then can you see here it was on the way up, and there it's on the way up the curve. Okay? It's generally best to look at these points as springs, okay, that stay still, and as the wave comes it goes up, down, up. So as it moves, can you see it's going to go up, 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 down, 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 all the way down and then back up. Okay? For those of you who've been and enjoy the sea, that's the kind of thing when a swell is going past you. You go up to the top and all the way down to the bottom. So the period over here is going to be equal to 4 seconds, right? T equals 4 seconds. All right. You could also have got this from here by saying, if you look here, I'm going down through there and I'm going down through there again. There's 4 seconds as well. 6 minus 2 is 4, right? So the period can also be, well, that's going to be 1 second there, okay, isn't it? From the top to the top, that's going to be 5. 5 minus 1 is 4 seconds, okay. The frequency, yep, they've asked us the frequency, and the frequency is equal to 1 over the period, which is 1 over 4, which is 0.25, and what do we measure it in? Hertz. Okay, we measure it in hertz. All right, let's get another page over there going. Right, and I can scroll back to get to this one again. So we say okie dokie. Then the frequency. The next question, let's have a look what the next question is. Frequency, what is the wavelength? Okay, question 4. Okay, wavelength, all right? Wavelength, now, we have to use the wave equation, which is the velocity is equal to lambda times frequency. Okay? Now we know the velocity is 2 meters per second. They've given it to us. The wavelength, we don't know. The frequency, we've just worked out. Therefore, the wavelength is going to be equal to 2 over 0.25. which is equal to 8 meters. Okay. Can you see? All you do is you put down what you're given and you keep going from that point onwards. The next question they're asking, number 5, what is the length A to B in the diagram? Well, let's have a look at A to B. Okay. What is the length A to B in the diagram? I need to go back to the previous question. I just remembered I forgot to answer something. But we'll look at it in the next one. The length A to B in the diagram. Okay. All right. The length A to B. Right. Now, what is the length A to B? A to B. Well, let's count. It's 1 and how many? It's going from, there is 1 wavelength, correct? And there is a half a wavelength. Am I right? Can you see? It's going up to the top. And there's 1 wavelength. Let's just do this on this thing. Okay. Let's just check here. Put this back over there. Right. Let's just follow the wavelength in blue. Okay. Let's just go. Can you see? We're going this way. There to there, to there, to there, to there. That is 1 lambda there, right? But my B, the A to B is A to B. Right? So it's 1 wavelength, and this one here is going to be half a wavelength, isn't it? This is lambda, and this piece here is going to be half of 1. Right? Am I right? Can you see? We're going up, down to there. That's the same as that, isn't it? It's how much of a wavelength? Okay? Okay. And you've got a wavelength, and there's 1 wavelength to there. There's a wavelength to there. All right. Sorry, to that point there. There's 1. Up to there, and we're going through. There's our wavelength. Right. So now B is sitting at a bit further on. How far on? Well, let's have a look. There's half a wavelength, isn't it? Because that's a full wavelength. So it is 1 and a. If your diagram shows there as B, some of them do show that point as B, that would make it 1.5 wavelengths, wouldn't it? I'll do both. Okay. If A to B shows to that point, let's say here, let's say B1 over there. Okay. That is 1.5 wavelengths. It's 1.5 lambda, which is 1.5 times by 8. All right? So you'll basically take 1.5 times 8, all right, which is 12. Let's look at it the other way. I know some of the papers that were downloaded at some stage, the B was at that point. So what have we got there? We've got, that's a half, that's another half. So that must be a quarter there, right? From there to there's a quarter. So that's 1 3/4. So I'll just change the color and we go to the other one. Is 1 3/4 wavelength is 1 3/4 times 8. And let's do that. 1.75 times 8 is equal to 14. So you have to go back to your diagram and you have to answer the question from there. Right? That's how you're going to do these. Okay. The next one. Okay. So remember, when you've got the wavelength drawn, you can go and put in the frequency, the velocity of the wave, all using the wave equation. But you have to go and actually count some wavelengths sometime, right? So you generally start with the point where it's at a specific point, either a crest or a trough or going through the middle, right? Then you find the other wavelength and work out what fraction of wave is after that point. Sometimes they might only give you 0.75 of the wavelength, but you just go and you count it from basics, right? All right, now the next question. The next question says, right, Person A stands 400 meters from person B, who fires a gun. If person A starts a stopwatch when they hear the bang, how accurate is their timing? Use the speed of sound in air as 340 meters per second. What is happening here is important, okay? Because you've got to draw it and think what is happening, okay? Person A and person at B, okay? This is how you draw these, all right? Right, a person at A stands 400 meters, right? So what do? I put in how far I am away. Like that, right? So this person here fires a gun. So I am going to have a sound wave coming to me standing over there. Yes, I do draw stickmen. All right? Now, therefore, what do? They've told us the velocity of sound in air is 340 meters per second. Okay? That's what they've told us. Well, what they want to do is they want to know what is the error? Well, what are they talking about? What they're talking about is that when you, okay, hear it, okay, and if you start your stopwatch when you hear the bang, all right, what's the actual error? In other words, how long does it take sound to get from there to you, right? Now, 400 meters is not that far away if you think about it, once around an athletics track, right? So let's have a look. How long does it take? Well, velocity is equal to distance over time. Okay, displacement over time, yes, but we'll get to that at some stage. Okay, so we know that we've got, therefore, 340 must be equal to distance over time. 400 over time. Therefore, the time it takes is going to be equal to, right, 400 over 340, which is 1.18 seconds. So it takes 1.18 seconds for the sound to get to me. Okay? So that person has been running already for 1.18 seconds. Okay? Well, take that as 100 meters. You can see it's linear. You divide it by 4, right? Which is almost 0.3, which is a long time in 100 meters, isn't it? That's a big error, okay, as a percentage error. Anyway, but all right. So that's what we're going to do with that. Okay? Now, the next section, the next question is question number 5. All right? How are we going to answer this? Your home receives power at 50 hertz as an alternating current. What is the wavelength generated by the transmission wires around us? Okay? So what they've told us here is they have told us that, okay, yes, they've said this. This is question 4. Okay? These wavelengths, these things over here, the transmission lines, okay, the frequency is given, and I think they gave us 50 hertz, right? Incidentally, what is the period? T is 1 over 50. Let's just have a look. And let's say 1 divided by 50 equals that, and the reciprocal equals, okay, 1 divided by 50 equals, and that 0.02 seconds. Okay? Right, just for interest sake. Anyway, now you know that velocity is equal to frequency times lambda. And they've asked us, they've said, what is the wavelength generated? How do we work it out? We know frequency, but we don't know. They've asked us for that one. So what do? Remember, this is electromagnetic, is it not? If it's electromagnetic, what do? We know that the velocity is equal to the speed of light, right? Therefore, we basically use C, which is 3 times 10 to the power of 8 meters per second. Therefore, 3 times 10 to the 8 is equal to frequency. Okay, So lambda is going to be equal to 6, which is going to be 6 million meters, which is 6,000 kilometers, like that. Okay, right, simple. Okay, so all we're doing with this is putting it in. We've only got one formula, guys. That's all we've got. Okay, let's have a look at question number 5. All right, question 5. If the sun were to suddenly stop all radiation, how long would it be before we can, on Earth, know about it? Okay, the sun is 148.7 million kilometers away. All right. Well, the question is quite straightforward. Question 5 is the sun is over here and we are over here. Okay. And we are 148.7 times 10 to the 6 kilometers away. Okay, this is the distance. All right, the sun is radiating, isn't it? Okay, so let's just put that in red just for some fun, shall we? Red, it's radiating heat and light at us, right? That's what it's doing. So we know how far it is, and let's put down our only equation that we've got. Okay, velocity is equal to frequency times wavelength. Okay, right, hold on, frequency, they've asked us time. So the only one that's connected is going to be frequency is 1 over time. But let's say we're unsure. Let's put down what we know. Well, first of all, we know the distance, okay? Oh, so what do? Okay, we can say to ourselves, okay, first of all, that distance there, we have to convert to meters, don't we? Okay, so how do we do that? Okay, right, we say to ourselves, right, distance is going to be equal to 148.7 times 10 to the 6 kilometers. But we must change this to meters. How do we change to meters? Well, remember kilometers, hectometers, decameters to meters. It's a length unit, so we're going down, which means we get bigger. So we times by 10, 100, 1,000. Okay, so we eventually end up with 148.7 times 10 to the 9 meters. Okay, now hold on. How do we go further? Well, you know that velocity is also equal to distance over time. It's measured in meters per second. Meters distance, time seconds. So what do we do now? Well, we know. Do we know the velocity? Yes, it's electromagnetic. It is C is equal to distance over time. So then we say 3 times 10 to the 8, because we don't know frequencies or anything else, do we? We know velocity, but we don't know wavelength either. 3 times 10 to the 8, okay, and we say that is then going to be, must be equal to distance, 148.7 times 10 to the 9 over time. We rearrange all of that lot, and we end up with a straightforward sum, which is going to be, let me just put this up. If we actually did it, you would come up with 495.6 seconds, right? Which is approximately 8.26 minutes. In other words, the sun could switch off, okay, and in essence, what do we say? We'd only know about it 8 minutes later. That is why light from distant galaxies, it's been traveling for millions of years. The picture we see now that you see from the Hubble telescope and in the magazines, that's what it looked like millions of years ago. Okay? especially if the galaxies are far away. Right, let's look at question number 5, all right? Question 5, oh, that's it. Sorry, we've done that one, okay? All right, okay. Then I'm going to leave that one because we just did it 8 point something minutes. Right, that's the first section, which is on electromagnetic waves, etc. Remember, how do we do them? If you've got the wave, even if it's a spring, okay? Remember, you find on a slinky spring, you find your big openings, and then it goes to that. This is a rarefaction, that's a compression. My favorite toy, here we go. That is a rarefaction. You can see the spring is open. This is a compression where it gets together. So you get that bit there and then an opening. Can you see it? Compression, rarefaction there. Compression and I hope it's showing up well, but that's what you get for those. And the wavelength is the same. You measure it the same way, okay? So you measure it crest to crest, compression to compression, rarefaction to rarefaction, trough to trough. Same thing, okay? And the same applies. Please remember the displacement, okay? One of the questions you will be asked more than likely, the displacement of these waves is in the same direction as the motion. Okay? Because if I push the slinky, the particles move backwards and forwards in the same line that the spring is moving. Those that have been through the actual lectures, let's say, with me, we've done quite a few of those, okay? Those kinds of problems as well. And we've spoken about that in detail. Remember, the waves, the transverse, guys, okay? Longitudinal transverse, the displacement is at right angles. This is the way it moves. This is the displacement here. Okay? Right. So we've been through that there. Oh, one other thing. Essentially, although I've said you have one equation, velocity is equal to frequency times wavelength. Okay, wavelength in meters, frequency in hertz, and velocity in meters per second. Remember, frequency is equal to 1 over the period. And the period is how many waves that you count going past you in a section of time. That's all it is. Okay, cool. Then next one we're going to carry on, and we'll carry on from question 6. That's going to be, we're going to start doing the electromagnetic fields, charges on particles, etc., etc. Okay, quite a cool section. Please, I know I keep saying it, please learn the definitions and the theory bits, etc. Okay, we're focusing mainly on the calculations and elements around those. Cheers, have a good one, bye.